Waves. Here are your priming questions. Oscillations. So far we've mainly focused on vibrations, so this will be something that's moving back and forth, and this is what we would call an oscillation in time. So if we think back to our pendulum, and it's just moving basically from here to here to here to here, or if we have a spring with a mass on it, it's simply moving up and down, up and down. Now, when we talk about an oscillation through space and time, this is when we're talking about a wave. And so this is when you probably think of your sinusoidal wave, and this is traveling in a certain direction at a certain speed. And what's interesting is all waves carry energy. We're going to talk about a lot of different types of waves through this, but things like sound and light and different types of radiation all have energy. And this is why these certain waves can also be dangerous for us, because they carry energy. So, wave structure. Most of you are already familiar with this, but as a quick recap, the wavelength is going to be the distance between two like positions on a wave. So here from the peak to the peak, we have our crest, which we also call peaks or ridges, and we have our troughs on the bottom. We have our origin through the middle. Our amplitude is going to be the maximum displacement, so it'll be from the origin to the peak or the trough. And if we have this wave moving in a certain direction, however quickly it passes a certain point per second is going to be the frequency. So, our wave equation. Some of you may already even be familiar with this equation as well. You might have seen it in a different form or with different variables. We are going to use V equals lambda f, where V is the velocity in meters per second, lambda, think of it as an upside down y, was the wavelength in meters, f is the frequency in hertz. So the velocity of the wave is equal to its wavelength times its frequency. And for those of you that have worked with electromagnetic waves before, the riddle here is what's new? It's c over lambda. We can talk about that in class. So, types of waves. We have electromagnetic waves. These are transverse waves that require no medium. And we're going to talk about what transverse means in just a little bit. So light travels at 2.99 times 10 to the 8th meters per second. That is very fast. This is what we consider to be the cosmic speed limit right now. We typically will round this to 3 times 10 to the 8th meters per second to make it easier to type into our calculators. We also need to remember is when you're working out your practice problems or your problems in general, we do not take this value for our significant digits. So even when you use 3 times 10 to the 8th, that doesn't necessarily mean that your problem will only have one sig fig. Okay? And this is in a vacuum. Light can travel through different mediums, and in different mediums, light will have different velocities. But in a vacuum, it's going to be roughly 3 times 10 to the 8th. And there are many different types of electromagnetic waves. Here is our spectrum, and you can see the shape of the sinusoidal curve or of the waveform here, and you can see the frequency gets higher over to the right. And this is with gamma radiation. And all the way on the left side with the really long wavelengths or low frequency, we have our radio waves to microwaves, infrared, our visible light, which is really only a very small portion of our spectrum, and then we go to ultraviolet, X-ray to gamma. Also, we give this value its own unique variable. So this is what we usually use for c, and that means the speed of light. It is a constant for us. Now, matter waves, this isn't that important. This is just to show you that there are some really interesting types of waves out there. Subatomic particles show wave-like behavior. They have a wave-particle duality, and we describe this using quantum mechanics. So if we were to look at an atom or look at multiple particles, they would have a wave-like nature as well, which is an interesting thing to think about. Now, what we're going to spend the majority of our time on are mechanical waves. These are waves which require a medium. They need something to be able to go through. For example, sound requires a medium. If you're in a vacuum, there is no sound. So when we talk about transverse in particular, this is when the force vibration is perpendicular to the direction of propagation. That sounds really complicated, but if you look at this, If our wave is propagating or moving to the right, a transverse wave will have the particles moving up and down. The easiest analogy is the wave, literally the wave at a sports arena. When you do the wave in the audience, you'll have people standing up, and the wave is moving across the stadium, but you as a particle of that wave are moving up and down. So that is a transverse wave. The other type of mechanical wave, or category I should say, is longitudinal. And this is when the force vibration is parallel to the direction of propagation. This happens in fluids, typically. And so that's what this looks like. If we were to compress a spring on the left side, the wave would propagate to the right by compressing and decompressing the spring as it goes along. This is another diagram that I found online. And you can see the particles themselves. As the particles are compressed on this left side, you see that wave propagate to the right, and you can see the motion of the particles, especially with the colored ones, that they move parallel to the direction of propagation, and you can see very clearly how the wave is moving through these areas of compression as we go down. Now, the next type, which is also a mechanical wave, is a surface wave. When you think of earthquakes or ocean waves, these are surface waves. And what's interesting about these is if you look at the individual particles, they're not transverse, they're not parallel. The particles themselves move in a circular fashion. And so the particles move in a circular movement as the wave passes beneath them. And this can be either through liquids or solids even. When we talk about solids or earthquakes, a lot of times we refer to these as Rayleigh waves. And you can see as the wave passes through the earth or the surface of the earth, you can see how the particles move. And this is why earthquakes are so destructive, because the surface of the earth is moving like that in a circular manner, and it's moving at a different rate at different parts, which is very destructive.